Hello everyone, and welcome to my presentation on the computer's most essential hardware, the CPU. My name is Zachary, and today I would like to go into an in-depth look on what makes a CPU and how it communicates with the rest of the computer to do what you need it to do. First, I should go over what the computer is and what makes it run. A computer is a programmable machine that can perform many different instructions that a user programs it to do. With the right hardware present on its motherboard, the computer is capable of a number of things. The motherboard, which is used to connect together the different hardware components, houses such things as the CPU, the brain of the computer, the RAM, the random access memory, which is the temporary storage space, the hard disk drive, the main source of storage, and the input-output ports for keyboards, mouse, monitors, speakers, etc. These are the basics of necessary computer hardware, though many modern computers these days also carry extra features, such as a GPU for advanced video graphics to help with performance in gaming. Now that we've briefly covered the insides of the computer, let us move to the main subject of this presentation, the CPU. As previously stated, the central processing unit is the brain of the computer. It is made up of a collection of subsystems that help it operate, as you see right here. I will briefly describe them now, but we'll go into more detail about some of them a little later. Starting from the top, we have the program counter, which is a 32 or 64-bit register that holds the address of instructional data to be processed next. Here we have L1 cache memory. Now, L1 cache memory can be either be inside the CPU or right outside the CPU. Either way, it is used to hold multiple amounts of instruction data from memory, the hard disk drive, so the CPU can quickly acquire them. Next we have the instruction register, which holds the current instruction data to be executed by the CPU. All these components that I'm describing are controlled by the control unit, controlling all the actions of the CPU's components. The CPU houses several registers that act as bytes of memory that can be used to hold data from arithmetic and logic operations from here, the arithmetic logic unit, or ALU. It takes in bits of data to perform logic gate operations and provide output to memory. All these components are connected with a bus interface, which is a collection of circuitries that connects the CPU to also other parts of the computer, like memory and input-output devices. Finally, in association with the ALU, we have the condition flags, which are used to hold such things as carry flags and extra data from the results of arithmetical operations from the ALU. With all these components involved, how does the CPU work? As previously said, the CPU uses the bus interface to interact with other components of the computer on the motherboard. The interface is also used to connect the components of the CPU together. The components inside are controlled by the control unit, which uses set and enable wires to activate them. For such things as registers that hold data, set wires are used to store data in a register, while the enable wires send the data along the bus interface until another register is set to activate. Not all registers on the CPU have enable wires, however. The circuitry that controls the bus interface is done with electricity that goes through different components used to handle the speed and the power of the electricity. The following can be found in logic circuits and the CPU's power supply. First we have resistors, which take in electric energy and convert them into heat as it attempts to go through the resistor. They do not hold an energy, but it helps slow down the current. Capacitors are electric fields that are used to hold an energy and change its voltage power over a period of time. Then we have inductors, which are magnetic fields that are used to hold an energy and change the speed of its current over a period of time. Unlike resistors or capacitors, inductors are usually only found in the power supply circuit of a CPU. We now want to get into exactly how the CPU performs. For starters, how does the CPU interact with memory? The CPU processes instructional data extremely fast, so much so that it works faster than it takes to grab data from memory. This is where L1 cache memory, or memory data register, come in. It holds in data to be processed, and therefore the control unit can grab the data just as fast as it can process it. When it is time to process instructional data from memory, the control unit, ALU, and condition flags come into play. You see, inside the control unit and ALU are a bunch of circuitries composed of logic gates. The basic logic gates are AND, OR, and NOT gates, which are pictured here. These tables help describe how each gate works. For an AND gate, each circuit must be turned on, set to a binary digit of 1, as you see in the truth table, to activate the gate. For an OR gate, at least one circuit must be on to activate the gate. And finally, for a NOT gate, which is this shape down here, usually we represent it by the dot, the circuit must be off to activate the gate. When put together to make either combinational or sequential logic circuits, they make many intricate operations used within the ALU and control unit. The ALU does many arithmetic and logical operations to process instructional data from memory. When it is done performing, processed data gets put into one or more data registers before either getting processed again or put back to memory. If it goes back to memory, it goes back to the MDR and waits for the memory address register, or link register, to have it sent back. The bus interface used here is set up into 3 parts: the address bus, the data bus, and the control bus. By housing data in a CPU register, you want to match the bit group in memory to the bit group of the CPU register. Therefore, the following needs to happen. The control unit puts the address of the wanted memory on the address bus. It then puts a copy of the register bit group on the data bus. Finally, a write signal is put on the control bus. Data is then put back to memory. Sometimes, data from the CPU cannot go back to the hard disk just yet, so it temporarily gets placed in RAM instead. It needs to make sure to eventually put the memory back on the hard disk before the CPU gets shut down, or else that memory will be lost forever. Now you are probably wondering, how exactly does the CPU use the control unit and ALU to execute instructional data? To execute programs, it all starts with the user. When the user uses an input device to get the program started, unstructured data is fetched from memory and put into registers on the CPU to be prepared for decoding. The control unit houses decoder logic circuits that convert instructional data, which can be properly read, processed by the ALU, and executed by the instruction register. The ALU, which is made up of logic circuits such as adders, which are used for mathematical binary computations, and multiplexers, used to decide what bits of code are needed to pass through for processing, does multiple operations with the data to get it ready for execution outside the CPU. Certain operations, especially from adder circuits, bring about extra data or carry data, which gets flagged by different components of the CPU by a different component of the CPU, the condition flag component. The instruction data register then takes the processed memory bits to be executed and tallies the operation on the program counter. Program counter points to whichever instructional address is next, which will be held in the stack register until called. Once the current data is executed and taken to the link register, the counter sends the next processed instructional data to the instruction register, and it keeps going until all data has been processed. All executed instruction data is sent to its respective memory location or output device once finished. This method of fetch data, decoding and processing data, and executing data is a cycle that continues on until all the data needed to execute the program comes to a stop. The program appears on your respective output device of choice, and you're good to activate the next program or instruction. I want to thank you for watching my presentation on the CPU, and I hope it has been informative. If you care to read more about the CPU, feel free to view the citations I have here. These pages are where I acquired some images from, and much of the information that helped me explain all of this. Have a wonderful day now.